Section 690.63 of the National Electrical Code, or NEC, can indeed be applied to single-phase inverters used with wind generators. Its purpose is to ensure that connecting a single-phase inverter to the utility grid doesn't create unacceptable voltage imbalances, a concern that applies to all inverter types, including those paired with wind generators. Determining whether a system is designed to prevent significant unbalanced voltages involves considering several factors. The NEC itself does not offer specific methods, but there are widely accepted considerations. Firstly, the size and type of the inverter is a factor. Larger inverters have a greater potential to cause voltage unbalance compared to smaller ones. Furthermore, single-phase inverters are inherently more prone to creating voltage unbalance than their three-phase counterparts. Secondly, the impedance of the utility grid at the point of interconnection is crucial. A grid with high impedance is more susceptible to voltage unbalance issues than a grid with low impedance. Thirdly, the number of inverters connected to the grid matters. A larger number of interconnected inverters increases the overall potential for voltage unbalance. Fourthly, the presence of other loads on the grid can play a role. Loads that draw unbalanced currents can contribute to the problem. If any of these factors suggest a risk of voltage imbalance, mitigation steps are essential. Firstly, consider using a three-phase inverter, as they are less likely to cause voltage imbalance compared to single-phase inverters. Secondly, interconnect the inverter to a grid with low impedance, which can be achieved by using a transformer or installing the inverter near the utility substation. Thirdly, limit the number of inverters interconnected to the grid. If a large number of inverters is necessary, a load balancing system might be required. Fourthly, install filters to reduce harmonics generated by the inverter, as harmonics can worsen voltage imbalance. By addressing these factors and implementing appropriate mitigation strategies, you can minimize the potential for voltage imbalance and ensure that connecting a single-phase inverter to the utility grid remains problem-free. When analyzing the inverter's size and type, consider the power rating and the technology used within the inverter. High-power inverters inject more current into the grid, increasing the likelihood of voltage fluctuations, especially if the grid is not robust enough to handle it. Different inverter technologies, such as transformer-based or transformerless designs, also have varying impacts on voltage quality. Transformer-based inverters generally provide better isolation and harmonic filtering but may be larger and less efficient. Transformerless inverters are more compact and efficient but require sophisticated control algorithms to minimize harmonic injection. When assessing grid impedance, it's important to understand that impedance is the opposition to alternating current flow. High impedance means that even small changes in current can cause significant voltage drops or rises. Utility grids typically have varying impedance levels depending on the location, the capacity of the local infrastructure, and the distance from the substation. You can consult with the utility company to obtain impedance data at the point of interconnection. Alternatively, specialized equipment can be used to measure grid impedance directly. The impact of multiple inverters on voltage imbalance is cumulative. Each inverter, especially single-phase units, introduces some level of voltage imbalance. When numerous inverters operate in close proximity on the same grid segment, their individual imbalances can add up, leading to a more significant overall imbalance. This is particularly problematic in areas with high penetration of distributed generation, such as residential solar installations. Load balancing systems can help mitigate this issue by actively managing the power output of individual inverters to distribute the load more evenly across the three phases of the grid. Regarding unbalanced loads, these are loads that draw different amounts of current from each of the three phases. Common examples include single-phase motors, electric heaters, and lighting systems connected unevenly across the phases. These unbalanced loads create unequal current flow, which in turn leads to voltage imbalances. To address this, utilities often try to distribute single-phase loads evenly across the phases during the planning and installation stages. However, in dynamic environments with constantly changing load patterns, maintaining perfect balance is difficult. Installing filters to reduce harmonics is another crucial step. Harmonics are voltage or current waveforms that are multiples of the fundamental frequency, typically 50 Hz or 60 Hz. Inverters, especially those using switching power electronics, can generate harmonics that distort the voltage waveform. These harmonics not only contribute to voltage imbalance but also cause other problems such as overheating of equipment, interference with communication systems, and reduced power quality. Harmonic filters are designed to attenuate specific harmonic frequencies, thereby improving the overall voltage quality and reducing the risk of equipment malfunction. There are two main types of harmonic filters: passive filters and active filters. Passive filters consist of inductors, capacitors, and resistors tuned to specific harmonic frequencies. They are relatively simple and inexpensive, but can be less effective under varying load conditions. Active filters use power electronic components to actively inject current that cancels out the harmonic currents generated by the inverter or other loads. Active filters are more expensive and complex but offer better performance and adaptability. When interconnecting an inverter to a grid with low impedance, the goal is to minimize the voltage fluctuations caused by the inverter's output. A grid with low impedance can absorb changes in current without significant voltage variations. Using a transformer can help reduce impedance by providing a step down in voltage and a corresponding increase in current capacity. Installing the inverter close to the utility substation also lowers impedance because the substation typically has a high capacity and a robust connection to the main transmission network. Another consideration is the use of advanced inverter control techniques. Modern inverters incorporate sophisticated algorithms that can actively regulate their output to minimize voltage fluctuations and harmonic injection. These techniques include reactive power compensation, voltage regulation, and harmonic current mitigation. Reactive power compensation involves injecting or absorbing reactive power to maintain the voltage at the point of interconnection within acceptable limits. Voltage regulation dynamically adjusts the inverter's output voltage to compensate for voltage drops or rises on the grid. Harmonic current mitigation actively shapes the inverter's output current to minimize harmonic distortion. In addition to these technical measures, proper planning and coordination are essential for managing voltage imbalance in systems with distributed generation. This includes conducting thorough grid impact studies before installing new inverters, coordinating with the utility company to ensure that the grid infrastructure can accommodate the additional generation, and implementing monitoring systems to continuously track voltage levels and power quality. Grid impact studies involve simulating the behavior of the grid under various operating conditions to identify potential problems and evaluate the effectiveness of mitigation measures. These studies typically consider factors such as the size and location of inverters, the characteristics of the grid, and the expected load patterns. Coordination with the utility company is crucial to ensure that the interconnection meets all applicable standards and regulations. The utility company can provide valuable information about the grid's capacity, impedance, and voltage profile, as well as any specific requirements for interconnection. Monitoring systems provide real-time data on voltage levels, current flow, and power quality. This data can be used to detect and diagnose voltage imbalance problems, evaluate the performance of mitigation measures, and optimize the operation of the grid. In summary, managing voltage imbalance in systems with single-phase inverters requires a multifaceted approach that includes careful consideration of inverter characteristics, grid impedance, load patterns, harmonic distortion, and advanced control techniques. Proper planning, coordination, and monitoring are essential for ensuring that the interconnection of inverters does not compromise the stability and reliability of the grid. Furthermore, the selection of appropriate equipment and the implementation of effective mitigation measures can minimize the potential for voltage imbalance and ensure the safe and efficient operation of distributed generation systems. The NEC provides a framework for ensuring electrical safety and performance, but it is up to engineers and installers to apply the code in a responsible and knowledgeable manner. Staying up to date on the latest technologies and best practices is essential for addressing the challenges of integrating renewable energy sources into the grid. As the penetration of distributed generation continues to increase, the importance of managing voltage imbalance will only grow. By taking proactive steps to address this issue, we can ensure that renewable energy systems can be integrated seamlessly into the grid, providing clean and reliable power for the future. When assessing the potential for voltage imbalance, it is also important to consider the long-term impact of distributed generation on the grid. As more and more renewable energy systems are installed, the grid may become more susceptible to voltage fluctuations and other power quality problems. This is especially true in areas with weak grid infrastructure or limited capacity. To address these challenges, utilities are investing in grid modernization projects that include upgrades to substations, transmission lines, and distribution systems. These upgrades are designed to improve the grid's ability to accommodate distributed generation and maintain power quality. In addition to infrastructure upgrades, utilities are also implementing advanced control and monitoring systems that can actively manage the flow of power on the grid. These systems use sophisticated algorithms to optimize voltage levels, balance loads, and mitigate harmonic distortion. Another important trend in grid modernization is the development of microgrids. Microgrids are localized energy grids that can operate independently from the main grid. They typically include a mix of renewable energy sources, such as solar and wind, as well as energy storage systems, such as batteries. Microgrids can provide a number of benefits, including improved reliability, reduced greenhouse gas emissions, and increased energy independence. By operating independently from the main grid, microgrids can also help to isolate voltage imbalance problems and prevent them from spreading to the rest of the grid. In conclusion, managing voltage imbalance in systems with single-phase inverters is a complex issue that requires a comprehensive approach. By considering all of the relevant factors, implementing appropriate mitigation measures, and investing in grid modernization projects, we can ensure that renewable energy systems can be integrated seamlessly into the grid, providing clean and reliable power for the future. It is also important to note that the NEC is constantly evolving to address the challenges of integrating new technologies into the electrical system. The NEC is updated every 3 years, and each new edition includes revisions and additions that reflect the latest advancements in electrical engineering. Therefore, it is essential for engineers and installers to stay up to date on the latest version of the NEC and to be familiar with all of the applicable requirements for distributed generation systems. Finally, it is important to emphasize the importance of safety when working with electrical systems. Voltage imbalance can create hazardous conditions, such as overheating of equipment and increased risk of electrical shock. Therefore, it is essential to follow all safety precautions and to use appropriate personal protective equipment when working on or near electrical equipment. By following these guidelines, we can ensure that renewable energy systems are installed and operated safely and reliably.